Okay, first question. Yes.
In the definition of the Taylor series in 3 dimensions, you mentioned something about order for dxi and dxj. What was that?
Oh, just when you, what does it mean to do d squared f dxi dxj? And so if the function is c2, if it's twice continuously differentiable, it doesn't matter which order you take the partial derivatives.
Okay, so we have to just include that in our definition.
Well, no. The definition makes sense even if the derivatives are not continuous. It's just if the derivatives are not continuous, d squared f dx dy is not necessarily equal to d squared f dy dx. It may be equal, but you need the function to be c2, twice continuously differentiable, for that to be forced upon you.
Okay.
Next question.
How would you define what it means to have a local maximum at 1, 2, 3, 2?
Okay, so local max x naught means for all x close to x naught, f of x is less than equal to f of x naught. It's a local maximum. If you move a small bit away from it, the function can't get larger.
And close to arbitrary.
Well, and close by that, you could mean rigorously, there is an epsilon greater than 0 such that if the length of x minus x naught is less than epsilon, then f of x is less than equal to f of x naught. And that's a way to quantify what you mean by epsilon, by close. So if you're within a small distance, then you're not larger. So your function could look something like this. And this is a local maximum. It's not a global maximum. A global maximum means no matter what x you put in, it can't be larger. It could be the same value, but it can't be larger. So this definition has nothing to do with differentiability. It's purely a statement about the size of the function. In order to find where these local maximum or minimum occur, what would you love to have? If you had your choice, what kind of function would you like to look at? Differentiable. If you have a differentiable function, you have ways to try to find local max and local min. One way is to look for critical points. If you have some constraints, another way is to look for Lagrange multipliers. And so if you have the tools of calculus at your disposal, you have ways to search for it. If your function is even continuous but not differentiable, maybe you can do something like the divide and conquer method. In 2 dimensions or higher, this could be a little bit more involved. Okay, next question. Yes?
What is it? I have a loose definition of what it means to be simple, but what's the rigorous definition of a simple function, or what it means for a region to be simple?
So region to be simple means, so there's vertically simple and horizontally simple. I always forget which one is which. Is horizontally, if I start in the horizontal and I move, as I'm walking horizontally. So horizontally means I have 2 kind of curves like this. And so here is x1 of y, x2 of y. And so I enter the region, I stay in the region, and then I leave the region and I never come back. So that's what it means to be horizontally simple. Vertically simple is the other way, is that I walk in, I enter the region, I stay in it, and then I leave, and I never come back. And these are just very tractable for doing integration. These are very nice regions. It doesn't mean we can integrate the functions in closed form and use the fundamental theorem of calculus, but these are very nice regions for integration. So here, for instance, let's call this C and let's call this D. I could then write the integral y goes from C to D, integral x goes from x1 of y to x2 of y, f of xy dx dy. So the advantage of having simple regions like this is that it becomes very easy to write. You can stand with me. It becomes very easy to just write down. It becomes very easy to just write down the integration. If I give you a more complicated region, I don't know. We could do like a Rorschach test, and I could ask you, and what does this make you feel? Yeah. If you wanted to do an integration like this, how would you do this?
You have to split it up.
You'd have to split it up. You have all these kind of pedals. I mean, over here, this is the nightmare where you come in, leave, right? And so you have to keep splitting it up into simple regions. In each simple region, you can do things and then try to piece it together. Or you could do a Monte Carlo technique, just throw a bunch of dots. But throwing dots is not exact. It's extremely unlikely that you'll get a bad answer if you throw enough dots, but it's not a rigorous answer. The other thing is, especially in subjects like economics, you want to get closed form expressions in terms of your parameters. When you're throwing dots, you lose the ability of getting closed form expressions in terms of parameters. If you can evaluate the integrals directly, you have a chance. What else?
Could we quickly go over how you know whether or not to use the root test and the integral test and the comparison test?
Yes, it's the baby crying. So if a baby is crying, you have your laundry list and you just keep going down them.
Okay.
If there's one that you like more than the other, start with that.
Okay, so there are no indicators.
Well, there are indicators. A lot of it is experience. The more of these problems you do, the easier it gets to, oh, that's the baby is hungry versus the baby has a wet diaper. Okay. Some of them is you have some really good indicators. If you can look at it and you can see what looks like a sequence that's larger term by term that converges, or you can see a sequence that's small term by term that diverges, that's a strong indication to use a comparison test.
Right.
So if I give you something like the sum of n to the fourth over 2 to the n, I know exponential functions, and 2 to the n has exponential growth. Remember, 2 to the n is e to the n log 2. This function is going exponentially. This function is going polynomially. I expect the denominator to be winning over the numerator. The problem is, how do I rigorously compare all of this stuff? And so this is where you can do it with the comparison test. It would be a little bit of a pain. You could write n is e to the n. I'm sorry, e to the 4 log n. No, I'm sorry, n to the 4th is e to the 4 log n. And so now I would have e to the 4 log n over e to the n log 2. This is 1 over e to the n log 2 minus 4 log n. If you do a little bit of work, eventually I think you can show that this is going to be at least n over 1,000. So this would be then less than or equal to 1 over e to the n over 1,000 if n is big. And the reason is, for very large n, this is insignificant relative to this. This is going to be no more than half of this. So for really large values, this is looking like 1 over e to the n of 1,000. Oh, well that's just 1 over e to the 1 over 1,000 to the n. What series is that?
Geometric.
Geometric. Is the ratio greater than 1 or less than 1?
Greater.
Greater. Converges. So we did it by the comparison test. Would you want to do this by the comparison test on an exam, or is this a hard comparison to make? See, this is a hard comparison to make because you're young. I have been doing these problems for longer than you've been alive. When you do the problems this many years, it does get boring, but you can look at them very quickly and see what's going on. I have a lot of experience doing stuff like this, and it's now just instinctive, second nature, it's just going on in the background. What would you do for this one? Because the comparison doesn't look easy. I don't really know how to compare the n to the 4th and over 2 to the n with something I know converges. What would you try?
The root test.
Root test
Or the ratio.
or the ratio test? Which do you think is easier to use?
Ratio?
Could I just quickly, how did you get to e the n over 1,000? Where did that come from?
Oh, well, I'm saying this is where you have to be a little careful. If n is big, 4 log n is less than 1/2 n log 2.
Okay.
So n log 2 minus 4 log n will be greater than or equal to n over 1,000. Because I know the log of 2 is about 0.69, half of that is about 0.345, so 1 over 1,000 is going to keep me very safe.
Okay.
So this is just you doing some fancy algebra, knowing some things, being able to just look.
Okay.
Do you want to do this with ratio test and root test right now?
If other people think it'd be helpful.
I saw at least
Yeah.
2 more nods.
Yeah.
So either people want to see that, or people have had late nights and are falling asleep already. So again, always write things clearly. Root test. Let rho equal the limit as n goes to infinity of an to the 1 over n. If you write down what you're doing step by step, you are less likely to make a mistake. And you're more likely to do things in the right way. Keep the word limit. Don't just have things floating. So this is the limit as n goes to infinity of n to the 4 over n divided by 2 to the n to the 1 over n. I'll do it slowly. This is the limit as n goes to infinity of n to the 4 over n divided by 2 to the n over n. This is the limit as n goes to infinity of n to the 1 over n to the 4th over 2. And I'm just flipping the exponents because we've seen n to the 1 over n before. So the denominator is nice, it's just 2. So this is just 1/2, and now by the product rule, it's the limit as n goes to infinity of n to the 1 over n to the 4th power. We've calculated n to the 1 over n. What is the limit of n to the 1 over n as n goes to infinity? So that's a limit you need to know. So what does that limit equal? Somebody should know in this room.
0.
So let's take n to be a number like 5, 6, 7. N is growing. You're taking higher and higher roots. So you're saying this is going to get all the way down to 0. No. What's the smallest number? It can't get smaller than what?
1.
It can't get smaller than 1 because you're saying what number raised to the nth power equals n? Well, since n is getting very, very large, if my number were less than 1, there's no way the product could equal n. So n to the 1 over n has to be at least 1.
Does it converge to e?
But when if you had like 5, wouldn't 5 squared or the 5 root 5 be less than?
Can't be less than 1.
Okay.
So again, if you have n to the 1 over n equals x, that means x to the n equals n. It means x equals n. It means n copies of x equals n. So if n is greater than 1, these numbers have to be greater than 1. So it turns out that this limit is equal to 1. We saw that by noting n to the 1 over n is e to the 1 over n log n. And then we use L'Hopital to say the limit as n goes to infinity of log of n over n is the limit as n goes to infinity of 1 over n over 1 is 0. So the limit as n tends to infinity of n to the 1 over n is the limit as n tends to infinity of e to the 0, which is just 1. So n to the 1 over n, that's something you need to know. And so if you use that as 1, if we now come back to here, 1 to the 4th is just 1. So this would just give you 1/2. So that's how the root test would tell us that this series converges. It turns out we can actually compute the exact value of the series. It uses one of my favorite techniques in mathematics called differentiating identities. And you can get an exact value for this. Any questions on how we would use the root test for this? Yes?
So the root test, if it's greater than 1, it's divergent.
It diverges.
Less than 1, convergent. 1, no.
No information, right? The way you should look at it, the root and the ratio test are comparing your series to a geometric series. And the row is telling you which geometric series to compare it to. Okay? And so really the ratio test and the root test, they're doing a comparison test for you, but they're finding the right geometric series for you. They're saying, what would be the best geometric series to compare to? Let me use that. Okay? Any questions on how we would use the root test for this?
Could we maybe just do it really quickly here?
We just did. Oh, I'm sorry.
Ratio. Did you
Oh,
mean
sorry.
ratio?
Ratio test, yeah.
Then
No, I'm happy to do the ratio test now. Okay. So now let's do the ratio test. And again, start off by writing things carefully. So ratio test is going to be the limit of an plus 1 over an. So this is going to be the limit as n goes to infinity of n plus 1 to the 4th divided by 2 to the n plus 1 over n to the 4th over 2 to the n. And now it's just algebra. Calculus is done. That's one of the things that makes these tests hard to use. So this is now the limit as n goes to infinity. Well, I have n plus 1 to the 4th over n to the 4th. This is n plus 1 over n to the 4th. I have divided by 2 to the n plus 1. I have 2 to the n over here. So the 2 to the n comes up, and I have a 1/2. So this is just going to be 1/2 times the limit as n goes to infinity of n plus 1 over n to the 4th. Well, I can use the product rule, and that's like this.
So why is it 1/2 going to be 2 to the n over 2?
I mean, if you want to, I could write it more slowly as 2 to the n over 2 to the n plus 1. Because here the 2 to the n plus 1 is in the denominator. This is now comes up to the numerator.
Oh, I see.
And so this is then going to give me a 1/2. And now I just use the product of the limit of a product is the product of the limits. Okay, how do I handle n plus 1 over n? What is that limit? Well, we've seen this many times. You could view this as 1/2 the limit as n goes to infinity of 1 plus 1 over n to the 4th. And now if you look at it like this, it's clear that this limit is going to just be 1.
Sorry, why is it 1/2 if you still have a 2 in the numerator? I'm just
I
not
have
understanding.
2 n times in the numerator,
Yeah.
and I have 2 n plus 1 times in the denominator.
Right.
So when I simplify this, I subtract the exponent and I have 2 to the n plus 1 minus n.
Okay.
So here, 2 to the n over 2 to the n plus 1 is 1 over 2 to the n plus 1 minus n.
So that's just okay.
Right, just the algebra laws.
I just didn't realize the coefficient. Okay.
Right, and now that's going to just be 1 over 2. And that's where it comes from. So the hardest part is doing the algebra. The more steps you show, the less likely you are to make an algebra mistake, and I am not going to try to figure out what algebra you are doing. If you show me your algebra, there are several people on the previous exams who multiplied incorrectly. I checked with Cam to make sure I was multiplying correctly. And when Cam and I got the same answer, I called that the right answer. And I did not subtract for a lot of people because they showed their work and said, okay, so they said 4 times 8 is 24, not 32. It was clearly written to tell what you were doing. I'm not going to take off points for something like that. But when you don't show your steps, when you just jump to an answer, there's nothing for me to look at. So I strongly urge you, write what you're doing, write what test you're using. Keep writing the word limit each time. If you drop the word limit over here, that's very bad. You're saying this equals this. No, that's not the case. This is a limit as n goes to infinity. This is a ratio at a specific value of n. These two are not necessarily equal. So you have to restore. Okay. There is one other possible way to try to find this, if this converges or diverges. What could you do?
Integral test?
The integral test. If you want, I will show you how to set this up with the integral test.
Yeah, that'd be great.
Yes.
So that comes out to 1, and then you multiply.
No, this comes out to 1, so the whole thing is 1/2,
Okay.
so it converges. Because rho is less than 1.
So it's the same.
It's the same.
Okay.
In fact, it's not surprising that it's the same ratio. It's not a coincidence that you get 1/2 in both. You get 1/2 though for very different algebraic reasons.
I just mean the one test. But
Right. It's really comparing it to the same geometric series. Okay. Do you want to see how to do this with the integral test? I will do this so long as you promise not to rush me with pickaxes, stuff like that. I'm sorry? Sure. Right. So we have an is n to the 4th over 2 to the n, and because I'm old, I'm going to write this as n to the 4th e to the negative n log 2. because I know I hate to write things in base 2. Thank you for doing it one more day. Okay? So I know I don't want to write things like 2 to the n if I'm doing calculus. I don't want to have to take derivatives or integrals of bases other than e. I need to come up with a function f of x. What is your thought for the function?
X to the fourth over e negative x log 2.
Right. So what I need to do is integrate from, say, 1 to infinity of x to the fourth e to the negative x log 2 dx. Okay, you've all promised not to rush me, okay? I will show you how to do this using the integral test. What am I going to have to use?
Integration with
Integration by parts. Now, the thing that's a little bit annoying is I've got this log 2. So I'm going to change variables. Let's let u equal x log 2. du is going to be log of 2 times dx. X goes from 1 to infinity. Where does u go from? Log 2 to infinity. So this is the same as the integral from log 2 to infinity. X to the fourth becomes u over log 2 to the fourth. E to the minus u dx is going to become du over log of 2. So I'm going to get a 1 over log 2 to the fifth, integral from log 2 to infinity, u to the fourth, e to the minus u du. And I now just have to show that this integrates to a finite number. How can I do this? So how can I show this integrates to a finite number? What technique would you use to evaluate this integral? Integration by parts. How many times?
Too many times.
Not too many times, 4 many times. 4 many times. Right? You'd have to integrate by parts 4 times. Each time you integrate by parts, you would decrease the exponent of u to the fourth, and the e to the minus u, that's just giving you plus and minus signs. And then when you evaluate things at infinity, the exponential is decaying at infinity so fast you're fine. Okay, so as a good exercise, evaluate this integral using integration by parts. There is a way to do this without using integration by parts. E to the u is 1 plus u squared over 2 factorial plus e to the 10th over 10 factorial plus dot 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 dot. Right? I'm being really safe. I don't have to do 10. I could do other numbers. E to the u is greater than or equal to u to the 10th over 10 factorial. Therefore, e to the minus u, which is 1 over e to the u, is less than or equal to 10 factorial over u to the 10th. Now, my integral from log of 2 to infinity of u to the fourth e to the minus u du is less than or equal to the integral from log of 2 to infinity of u to the fourth times 10 factorial over u to the 10th du. Hey, what does that integral look like? What's this integral look like? I've got u to the fourth 10 factorial over u to the 10th. This integral looks like 10 factorial over u to the 6th. So this is 10 factorial integral from log 2 to infinity of u to the negative 6 du. So that's 10 factorial u to the negative 5 over negative 5 at log of 2 and infinity. The negative sign means I switch the order of bounds. So I have infinity log of 2. But because I have u to the negative 5, at infinity it's going to be 0. And so this will just be 10 factorial over log of 2 to the 5th. It will give me a finite number. So this is a much more high-powered approach to solving this problem. Rather than evaluating the integral exactly, do we need to know the value of the integral exactly? No, we just need to know, is the integral finite? So I just need to approximate this integral well enough to know, is it plus infinity or is it not plus infinity? And to do that, I can just estimate things a little bit. Okay? So again, we've now solved it using the ratio test, the root test, the comparison test, and the integral test. We've used every single test to solve this problem. So for some of the problems, you can use any test you want. What do you think you should do if you start doing a test and it's not going well? Switch to another. Take a new piece of paper. Don't write it directly in the exam book. If you're not sure what's going on, take a separate piece of paper, write it first, and then switch. And did you have a question?
Oh, for the integral test, we just show that there's a finite number. You don't have to
All we have to do is show that it's a finite value.
Yes.
I didn't quite understand that kind of that middle step with e to the negative u equals whatever e to the u, and then you like flip.
Well, this is what e to the minus u is.
Yeah.
E to the minus u is 1 over e to the u. And so I'm basically just taking 1 over both sides. If e to the u is greater than equal to this, then 1 over e to the u is less than equal to that.
Okay.
So for this specific problem, would you say that the ratio test and the root test are by far the easiest?
I would say for this one, the ratio test and the root test are by far the easiest. And then I would say the integral test and the comparison test are harder.
Shouldn't that be negative e to the negative fifth over 5? Because
No, because I then flipped the bounds of integration. It was originally a negative 5. I then flipped the bounds. All right, I have time for one more question because I'm already going to be cutting it short to get to the airport. One last question.
You said there's no linear approximation. Does that mean there's tangent plane approximation, or is that not a question?
Other than maybe as a definition, if I said there's no linear approximation, I would say there would be no tangent
No
approximation.
general approximation.
No general approximation.
What's the best way to study?
Um,
Well,
best way to study is to make your own study guide. I've posted a study guide,
Right.
but make your own study guide. Write down definitions. Look at the old exams. Look at your homeworks. Get a good night's sleep. If you want, bring some water or some chocolate or something like that.
The exam is in Physics 203,
The
right?
the exam is in Physics 203.
At 9:30.
Right. That does not mean you can divide by 0. Okay? Just because you're in a physics building does not mean you can divide by 0.
The psych professors would not be happy that we're taking it in a different place than we